conference. I hope everyone recovered well from last night. We have a great cast of speakers this morning, and we'll start with Sara Anna, and she'll be speaking on the concentration interval for the Lasso. Sarah?
Thank you very much. And thanks to the organizers for inviting me, and for, thanks to Axel. He was sitting next to me last week in another workshop, and he said, "Would you like to give a talk?" So, thank you, Axel. It's very nice to have this opportunity. So let me go to the next slide. Yeah. So I'm going to consider the Lasso and concentration type of results. So that's for the linear model, which you all know very well, I guess. But just to make sure we are agreeing on the notation, we have a response vector y, a data matrix x, n times p, and y is a linear function of x, so a linear combination of the columns of x plus noise. And then beta here is unknown. It's a p-dimensional vector, and epsilon is noise. Now I'm going to consider lower bounds, so the assumptions I make are not, so I'm for lower bound assuming known variance is not so bad, because I mean lower bounds will probably be higher, deeper if you know less. Okay, so I can, just to make life simple, I assume Gaussian noise with known variance. So p is the number of variables and n is the number of observations, okay? And p is typically much larger than n. So this is the type of goal I'm going to consider. So I look at the Lasso, that's minimizing the sum of squares. So the L2 norm squared. And then a penalty, which is of, well, proportional to the L1 norm of the coefficients. And lambda is the tuning parameter. So I assume most of you have seen this procedure. And my goal is to prove that the prediction error of this estimator lies within a certain interval with large probability. And here this is just the standard normal distribution function, and I want then to be in this interval where the boundaries are close to each other, as close as possible. Okay, now, so we can be very quick on that. Oh, there we go. So if you define the median of the prediction error, so this is a random variable, and this random variable has some median. Okay. Then by concentration of measure, if you replace here m minus and m plus by the median, this is just true. That's just concentration of measure. So we're done. I have m plus and m minus equal to the median, and I'm done. But that does not really help me very much, because who knows what this is? This is a complicated object, right? So I want to have more precise expressions for this median, or at least some bounds. And there are upper bounds. These have been developed for the last 20 years. But now I'm interested in lower bounds. I'm especially interested in this lower bound here. And then you can ask, why? Why do you want lower bounds? Well, for me, I need some lower bounds because I want to prove in another paper, so like efficiency of linear functionals. And for that, these are Kramer-Rauer lower bounds. You need also lower bounds for the Lasso. Then you can ask, of course, the question, why do you want to prove efficiency in Kramer-Rauer lower bound? Okay, you can keep on asking such questions. Why do you want to prove something? And that's indeed a good question. But I think it's interesting. Probably you know for the Lasso you need these. Well, you use these restricted eigenvalues all the time. And then you can ask, is that necessary? And the answer is already there. There's a paper by Martin Wainwright and other people saying restricted eigenvalue conditions are necessary if you want to have a polynomial time algorithm. But now if you do the Lasso, and you teach that in your class, and then a student asks, you give this result, so oracle inequality, and the student asks, is it necessary to have these restricted eigenvalues there? And then if you can just say, yes, I also have this lower bound where they appear again, that's somehow an easier answer than saying something about polynomial algorithms and so on. So that's why I thought, okay, let's see where these restricted eigenvalues also pop up in the lower bounds. Okay, that's the goal for today. Okay, so this is more or less the type of result. Let S0 be the active set of the coefficients, and the size of the active set is little s0, so the 0 is always for pointing to the true parameter. If the coefficients are sufficiently large, the non-zero coefficients, and the tuning parameter is chosen of the right order, well, nothing special there, just the usual thing, then the lower bound and upper bound behave like this. So it's just the number of active variables divided by sample size, the tuning parameter popping up, but here come now these, well, something like restricted eigenvalues, and I call them compatibility constants because it has to do something with the compatibility with the L2 norm with the L1 norm, that they are compatible to each other. So this is just an informal statement where we were heading at, so I have to explain what these compatibility constants are. And also if I give my results later on, the normalization will be roughly that you take your tuning parameter like this. Okay, so let's go back one slide. So I have here the L2 norm. This behaves like n, so usually you divide by n, and then you have to divide this by n, and then you get a different normalization, so I do it like this. Okay. Now, let's go back a few slides here. What I'll first do is just cancel the noise, and then see what happens to the lasso. That makes life much easier, but it's maybe not so interesting. So let me give a justification why looking at the noiseless case first is also of certain value. And the result, what I have here is actually for random design, for deterministic design, I don't have this kind of results. So let's just briefly look at random design. Suppose the rows of my X matrix, so that's this big matrix, suppose the rows are all, these are row vectors, this is NP, that's X. And suppose such a row, these rows are IID, Gaussian, with a certain covariance matrix. That's this. So these are p-dimensional vectors. The covariance matrix is p times p. And then just do the noiseless version of the lasso. So you replace this quantity, the x, by its theoretical or its population counterpart, and then do the lasso, and there's no noise. Of course, you can't do this in practice because you don't know this sigma 0, and that's the end of the story. You don't know, and there's noise. Okay, so this is a theoretical object, this blue beta star. So I gave them a color now because there will be 3 betas running around, so to distinguish them. Now I'm going to say, okay, this quantity sort of will represent the bias, and the distance to this noiseless lasso will represent the variance. So, of course, you have the triangle inequality. So this is the prediction error of the lasso with noise. And this is the prediction error of the lasso without noise. I replaced here the x because to make them just comparable, not this one, but the empirical version. And then you have the triangle inequality, okay? So if I can prove that this square root variance term is smaller than the bias, then it's actually the bias which dominates the problem. So if I then have lower bounds for the bias, I have it also for the noisy version, because the variance is of smaller order. So this theorem says, well, at least under this assumption, you need a largest eigenvalue, but not of the empirical matrix, but of the population covariance matrix. If that's bounded, so I should normalize, I didn't write it properly. So this matrix, assume that the entries in this matrix are bounded, and then that this eigenvalue is bounded. And then some compatibility conditions, which I have to explain, says that here it is. This is the variance, square root variance, is of small order of the bias. Okay? So now I can just first look at the noiseless case, and then it automatically results go also for the noisy case. At least in the case of random design. Okay, so let's see. What are these compatibility conditions, constants? Well, first some notation, beta S. So S is a set, and you look at a vector B, which is p-dimensional. And then you look at the subset of the variables. So they can be anywhere, but just for the case of the picture, say these are the variables S, and I call that Bs. And this is the remainder B minus S. Okay, but they can be sort of mixed they need not be so nicely ordered. Okay? Okay. Then the compatibility constant is defined as the minimizer of this quadratic form, subject to this restriction. Now, I don't think I can really go into too much details, but that's the way it's defined. So this is some kind of minimization problem which is non-convex, because it's really very non-convex in this part of the problem. And but I'll give you an example later on. For the total variation, you can actually compute it in some cases, if you know S. Okay? And let's say the minimizer, let's say the minimum is attained at some beta star. So this is the compatibility constant. It's much, in a sense, weaker than restricted eigenvalue or earlier versions of the compatibility constant. It's really an improvement. And I refer to these papers. They invented this improvement. So this is something to remember. Maybe I'll put it here. The compatibility constant is denoted by K squared. So this is a normalization. This normalization sort of makes sense by the size of the set S. This is the side of the set S. And then you get the L2 norm. And then the restriction is the L1 norm inside the set S is larger than the one outside the set S, and their difference is actually 1. Okay. Now this is my geometric contribution to the talk, to the workshop. It says that if this constant is it's positive, but if it's strictly positive, then the solution will have all strictly non-zero coefficients inside the set S. And let me prove that. Forget it for a moment. This makes it a little bit complicated. So forget for a moment about this part of the problem. Okay? Now let me see. I don't know if you can see it, otherwise I'll go on there. Because of the... let me go on there. Okay. So you're more or less familiar with the Lasso, but I do now the noiseless case. Let's do it this way. Well, let's put 1 So you are on the boundary, you can put less than or equal to 1, but let's put 1 here. That's the Lasso, it's a restriction on the L1 norm. And then also, Becca, they showed this picture. You have this L1 ball, and then you get sparsity because of this picture. Let me see if I can draw it. And then you can have sparsity in the solution, okay? But if this thing is inside here, then the story is completely different. So the worst case, let's say it's here. Say this is your beta 0. So this is gone. Okay, and if you then take this ball, well, I can't really draw it, but let me just draw a ball. The smallest ball, so if you take the ball larger, okay, you can have the L1 norm 1, so you have to shrink it such that it touches this boundary, and otherwise it's smaller, and it will be totally non-sparse. It will never be true that you then end up in such a corner. Huh? So it's optimal non-sparse. Yeah? Of course you have to prove this a little bit because it's in high dimensions, but this is what's happening. Okay, that's what this says. Okay. Yeah, so far so good. So that's important that this solution, B star was this solution, this solution of this scary non-convex problem. But at least we know that the solution will have this term, all components non-zero. So then I can define the sign of these components. They are plus or minus 1. So now I take S is the active set of the truth. And the sign is then well defined because they are non-zero. It's plus or minus 1. And then the condition on the size of the true beta 0 is like this. They have the same sign as this solution, beta star, and they're sufficiently large. And then the prediction error is like this. So it's an equality. It's not a lower and upper bound, it's just equality. Okay? Yeah, so maybe you wonder, what is this condition saying? I mean, sufficiently large can be way beyond bounds, but that's not true if you look at typical cases. So this condition, if you're lucky, if you can do a little bit, if a little bit play, you can play a little bit here, then it will say that the L1 norm of beta S will be bounded, say 1, maybe not 1, say 2, something's not going to infinity. So typically this will be the case, unless you have a very hopeless design. So that means they sum up to 1, so on average they will be 1 over the size of the set, 1 over S0. So if I multiply that by S0, on average that will be bounded. It can be that some are a little bit larger or a little bit smaller, but on average, okay? Now, compatibility constants, we usually hope that they don't blow up. That's usually you want this to be the rate of convergence, and you hope that this does not blow up, and there are lots of results how they behave. So let's assume that they are well behaved. Yeah, like a restricted eigenvalue, you don't want them to go to 0. That's what I'm assuming here. And then it was there, the lambda is square root n log p, so this is the behavior of that part. So roughly it's this is the noise level times some constant. So it is more or less saying the active component should be larger than the noise level, which is the usual beta min condition. Okay. So let's look at an example. So the total variation penalty. This is a special case where you have a function and you think its total variation is not too large. So you have your x data here and a function, and you measure it, well, it doesn't have to be equidistant at certain values. So you can call them whatever you like. So I call them not x1, x2, x3, but just 1, 2, 3 up to n, because it's just total variation. You can do any monotone transformation. So these are the values. F2 and so on. And then you look at the design. What is the total variation? And so that's just the sum of the absolute value of the increments of the function. Okay? And then we do least squares with a penalty on the total variation. And still no noise, just to make life simple, no noise. We only look at the bias. Okay, so that's again just a Lasso problem. Because you can just write any function value f3 as the sum of its increments, okay? That's what I'm writing here. So this is I call the coefficients. The increments are the coefficients, and these functions here are the covariables, so to speak. So these are just, how do you call it, heavy sign functions or something? These are the covariables, just half intervals. So I can just write the true function is a linear combination of these heavy sign functions and the noiseless estimator as well. So we just have a Lasso problem, okay? Now just a little remark that it doesn't matter. You just have a penalty on the increment, so where it starts, it's not penalized. It can go up and down. So there's one parameter which doesn't get a penalty, so that parameter is active. It would be a coincidence if it's 0. So the first parameter is always active. So you just say, okay, I put that also in the active set. So the active set is not just the number of jumps, but also the first parameter. So that's why I add one coefficient here to the problem. Yeah? So now I want to calculate this constant. So remember Rebecca's talks, she said, oh dear, if the covariables are very correlated, you're in trouble. Then the Lasso doesn't work. Now if you look at this problem, the covariables, they are there, the xj's. Let me just draw a picture again. So here's the x-axis. The covariables are like this. They are like this, say up to point j, and then like this. So if I take the next one, so they're almost the same, right? So the correlation between these two is more or less 1. So we're a highly correlated design. But that should not spoil everything. So let me see, what does the compatibility constant look like? So let me call the jumps d1, d1 plus d2, and so on. And d is the distance between jumps. So I'm assuming maybe that the function does not have too many jumps. The number of jumps I call s. So I'm assuming that the last jump is not just very much close to the last point, but a little bit away from that. And so the distance to the end point of the interval I call ds plus 1. And I assume just that the distance between jumps is an even number, so that I can divide by 2 and don't have to do complicated calculations. And then the compatibility constant is just the harmonic mean of the distance between jumps. Okay? So this is just a calculation. I probably have to think a little bit more why this is so, but this is what came out, the harmonic mean. And so this is this quantity, and the minimizer is here. It's proportional to the inverse of the distance between jumps. Okay? All right. So again, maybe I should say this is. So you may wonder, is this compatibility constant well behaved? Well, if you think if the distance between jumps is of order n, these are just numbers, okay? And there are s of them, so you average bounded numbers. You take an average of bounded numbers, and that should be also bounded. So this can be well behaved if the distance between jumps is large enough. Okay. Yeah, so you have a well-behaved compatibility constant, and without assuming like that you have other penalties like Rebecca had with the L2 norm. It's fine. It's just fine. And then, well, for the lower bound, you need to assume that the jumps of the true function are large enough, and then you get this exact result for the noiseless total variation least squares penalty. Least squares with total variation penalty estimated. Yeah, so you may wonder, okay, I'll come to the case of noise later on. So a little scaling, suppose that the jumps are equidistant or more or less equidistant, like here. And this is the tuning parameter. Well, then the prediction error behaves like the square of the number of jumps times log n. Yeah, so typically if you're thinking about these very smooth functions, they have only finitely many jumps, so you get the parametric rate. I haven't divided by n here. If you divide by n, that's the right normalization, then you get log n over n. You see it goes to 0. So and if s is bounded, you get the parametric rate. But this is also showing you how it behaves when s is increasing. Okay? Okay. Now the noisy case. Now it gets a bit technical. So here's the noisy case. This is the usual Lasso, Gaussian noise. Now what happens in the noisy case? Let me just say it in words. So you have this compatibility constant for the noiseless case, but the penalty is not for nothing. It has to do something. It is supposed to kill the noise. Okay, there's an epsilon term here and you want to kill it, to reduce the variance in some sense. And what that means that you have to pay a little bit here. So you lose here a little bit because of killing the noise. Here comes a constant, not 1, but smaller than 1. It could even be that you take different constants for different coefficients, so you get some weights here which are smaller than 1. But that's for the upper bound. If you have the lower bound, who knows, maybe this noise helps you. So maybe you can do better. It can be better with noise. There's no guarantee that noise always is bad. So you say, okay, it will happen with probability small, but I wasn't able to prove that. So I might also have some constants here which are larger than 1. So in general, I just put some weights there. And then you get this weighted compatibility constant. Okay? Okay? Yeah. Okay, now this is getting a bit technical, but I'll just try to give you the message. So if you have highly correlated variables, you're a bit afraid that these restricted eigenvalues or compatibility constants might blow up. On the other hand, what you have to kill is the noise, but not the clean noise, but only its projection after what's left over after projecting on the active set. So let me say this again. These are the non-active variables, and you project them on the active ones. That's this notation. And what's left over, the residuals or the anti-projection, are these. Okay, so if they're highly correlated, the active ones with the non-active ones, and then you start projecting, then there will be not so much left over. Okay, if they're highly correlated. So then this will be small. And this is sort of the variance of what is left over, the variance of the residuals. And I'm looking at what is on the diagonal elements, on the diagonal of this matrix. So the higher the variables are correlated, the smaller this will be. And I only need to kill the correlation between the noise and this residuals, which can be also very small if you have highly correlated variables. Okay, so that's what I'm doing here. I'm assuming that the tuning parameter is larger than these residuals after projecting, okay? So the anti-projection. So that can be small, and then you're happy. So correlated variables can be actually a blessing here. Okay, and this is just notation for later on. Okay, so I hope the message is a little bit clear. Okay, the upper bound then gives you this. Yes, so the upper bound is just saying, oh well, I have to give up a little bit here because of the noise, so I don't have the original compatibility constant, this one, but one with the weights here, but the weights are very close to 1, probably. Okay, so that's the upper bound. And that's this is not a new result. This is all in these papers. So the point is now the lower bound, and then, yeah, you can imagine that for each realization of the noise, you get different results. So I just have to look at what happens for all possible realizations of the noise, and then I get all kinds of versions of this. And then I just look at all those versions, and then I take the worst case, and that gives me then the lower bound. So this is more or less what I'm saying here, but don't look too much at the slides because you will get confused. I mean, the main idea is just just take a whole collection of weights. I minimize for all this whole collection of weights, and then I just take the maximal solution, and that will be then my lower bound for the true coefficients, and then you get this result. Okay, so so this is just the residuals of the projection on the active set, and this is the residuals of the anti-projection of the non-active variables on the active set. And this is the beta-min condition, and you get a lower bound where instead of, where it is, where's the upper bound? Here, the upper bound says, oh, here you lose a little bit, and in the lower bound I have no idea, maybe you are lucky, so you get a plus here. Okay. So let's look at the total variation penalty again. So here it is, but now with noise. Noisy total variation penalty, and the jumps are denoted in the same way as before. And then you can prove that this weighted compatibility constant with some weight here. Well, if the weight is less than 1 here, you lose something, and if it's bigger than 1, you can just put it to 1 and then it's okay. So you get this result. So it has something to do with the increments of the weights. It's a bound. Yeah, so you compare the weighted compatibility constant with the non-weighted one, and there's this relation. And then for this particular case, so when you have these very correlated functions, you do all these projections, and then you get your weights, and then Arnott and his co-authors did all these calculations. So for the upper bound, you can prove that the increments of the weights, you can bound them like this. And putting everything together, you get that if the jumps are sufficiently large, like I told you before, of that order of magnitude, then the total variation estimator has this upper bound, which was known, up to constants maybe, and this lower bound. So they are the same, up to a term here. And so if the number of jumps is bounded, then you lose a log term. But if the number of jumps is like a log term or a little bit larger, then you don't lose in order, and then they're of the same order. Okay. Okay. Yeah, so a few words about random design, just to go back to that. So deterministic design is of course important because this example with the total variation penalty is clearly deterministic design. So I can't handle that case with random design with this trick. But for random design I have this trick that you have this bias being of larger order than the variance. But then you need to, okay, so suppose the rows are Gaussian, IID Gaussian, with some largest eigenvalue. And then instead of putting here the empirical quadratic form, I put the theoretical one. Because if you random design, this would be a random variable, and it's not so nice. That's why I put the hat here. But now I have a population version without a hat. Okay, so that's just the same thing. And there's no n here, of course, because you normalize this by n, and then you get something which is on average the population version. And then I minimize this quantity, so that's the noiseless lasso again. Then you can prove the following result. So if the maximal eigenvalue is bounded, it may grow a little bit with log p. And if you look at the set S, whose size is not much larger than the size of the active set. Well, it can be larger, it depends on what this does here. Let's say this constant is bounded and this stays away from 0, this constant. Then this roughly says the size of this set S is proportional to the size of the active set. And suppose that then you still have convergence to 0. And so this is roughly the bound for the prediction error for the lasso with, if you put here the active set as 0, but I assume it's also still going to 0 for a little bit larger set. Okay, so that's my condition. If this is true, then for the usual choice of the tuning parameter, you get something precise. I've written here just that the variance is of small order of the bias. Okay, so if you now replace this empirical compatibility constant by the theoretical one, there's also a population minimizer called it beta star with this sign. Again, inside the set S it will be non-zero, so you can define the sign. And then if the active coefficients are sufficiently large, which is exactly like before, except now in the population version, then the prediction error of the lasso behaves like this. So you have an exact bound up to smaller order terms. Okay? And like before, this is just saying that its beta should be on average above the noise level. So let me conclude. So I gave this goal in the beginning. And if you have this, I wrote it here maybe, you can just put here the median, and then everything is done. And now I replace this median by the bounds that I have. And actually this concentration result with the median gives you immediately deterministic bounds for this median. This is a little bit playing around with probability. So as soon as you prove something with positive probability, you're done. And if something holds with positive probability, you get a statement which is about deterministic quantities, so then it's just true. Okay, that's these kind of tricks that you can play with concentration inequalities. So that doesn't really bring much, but at least cleans up the final statement. And you can make a final statement of this way. I can make it more precise if you want. I'm working on that. So it's just an order term here, but I can make it more precise. So it doesn't really, this is not new, but it looks more clean than all these complicated probability inequalities with all these constants running around and so on. So of course this order one will be not as small as that one. So you know it's really in a way cheating. It looks nice, but not really. And so it's really an interval, and this interval is of larger order than t. Okay. Should I say something? I think not. Okay. So just let me thank Rico Sencluze from ETH Zürich and Hamza Fafsi here from Cambridge for helping me with some problems I had with this non-convex optimization. And I thank the Isaac Newton Institute and put down this number. And Richard Samworth, I thank, of course, because he invited me here. And I want to thank you very much for your patience. Thank you.
So we have time for some questions.
Just curious, since you have this beta mean condition in these results, I mean, this is maybe not related to what you're talking about, but when you have this interval, I mean, in principle, one could ask to construct a confidence interval for this risk by somehow, you know, replacing m minus and m plus, maybe by some data-driven quantities. Under this beta mean condition you have, this might even be possible. So I'm just curious, can one use this argument somehow, maybe to construct a confidence interval for the prediction risk?
Yeah, I don't know. You have to somehow estimate the active set. You have to, if you want to calculate this thing, you have to know S. And that's of course not the case. So unless
under
you
the
assume
beta
loss,
mean condition, you can probably somehow do that.
you can maybe do a screening or something. Yeah.
So variables
It's
selection
very
should be cons-
not these beta. You need stronger beta mean conditions, and then yeah,
So you would need stronger ones.
probably yeah.
Any other questions or comments? Thanks.
Thanks.
Sarah, for an interesting talk.